uranium-238 undergo fission, turns into two equal fragments. Okay, so let's just write out a simple equation for this. 238 uranium, we are not given the charge number, so you can ignore it. So you need to know, right, that usually the fission process is accompanied by a slow neutron. Even if you don't know, also never mind. Okay, and usually, right, after it fuse finish, right, you give out another 2 or 3 neutrons. So for this case, right, we want to have 2 equal part fission products, right? So let's call that X. So what is the mass number here? Well, it will be around half of 238. Okay, so if it's around half of 238, it could be 119, it could be 118. So here, right, we are not so particular, so it could be 118 or 119. Okay, correspondingly, right, if it's 119, then you have one neutron release. If it's 118, then you have 3 neutron release. So I'll write it as 3 or 1. Okay, 10N. But this is not really important. Okay, therefore, right, the two fragments definitely must have mass of near 120. So this is correct. What about the let's do a statement by statement. So statement A, right, 238 cannot fission spontaneously. Okay, this statement is actually true. Yeah, because we actually need to have a neutron to trigger this fission. So fission process, right, is never spontaneous one. Yeah. However, right, it cannot be deduced from the information. So while it is true, it cannot be deduced. So A is not the answer. Okay. What about B? The two fragments, right, have mass number near 120. That's right. Okay, and have masses greater than half that of uranium. This is definitely false. Okay, so let's consider a case whereby it's 119. Even if it is 119, right, it will also not be possible. How do we know? Because, right, we look at the binding energy per nucleon graph. Okay, so which looks like this. So this is Be per nucleon, and this is the nucleon number, which is the A. So where is uranium? Uranium will have been somewhere here. Okay, so this 238U. Suppose, right, it turns into the 119, so that we can compare the number, right. I mean, if it's 118, right, then it's definitely not possible. Yeah. So what if it's 119? If it's 119, right, also not possible, because, right, sorry, it's not X, this is not U, this is X. Even if it's 119, right, the fact that this guy got greater binding energy per nucleon compared to uranium, right, means that it has greater binding energy. Greater binding energy, right, means what? If you have a chart, right, that shows a mass. So on one hand, right, we can say we have 238 nucleons. 238 nucleons have this amount of mass. Okay, when they form uranium-238, right, the mass will have been smaller. Okay, so this is 238 uranium, and the binding energy is this amount. Okay, but because, right, binding energy of X is even greater, that means, right, X must have a greater mass defect. Greater mass defect, right, means that it must have less mass. Okay, yes, less mass. This is why, right, binding energy is used to figure out whether energy is given out or not. Okay, yeah, because, right, we are comparing the mass energy through the lens of binding energy. Okay, so with this, right, we can tell that statement B, since energy is since the binding energy of X, right, is greater, X must have greater mass defect, X must have lesser mass, and thus, right, statement B is false. Okay, and finally, right, statement C and D, one is more than 7.6, one is less than 7.6. So we know, right, that as uranium fission, okay, it must have turn into something with a greater binding energy. So it has to be D and not C. Okay. If you are keen to find out why is it 8.5, right? How could we calculate that? Well, you see, in this reaction, right, the energy release will have been 200 MeV. Okay, so the delta E, right, is equals to 200 MeV, and that is also equals to, right, the 238. Sorry, I should have taken it as 118, right, or 119. So let's just take it as 118.5 since I don't know which one it is. 118.5 times binding energy per nucleon of the X. Okay, this one minus 238, okay, times of 7.6. Yeah, so if you solve this equation, right, so let's call this quantity small x. Okay, so you have 118.5. And you need to multiply by 2. So 2 times 118.5 times small x minus 238 times 7.6 equals 200. Solving this equation for x, you'll get x is roughly 8.5 MeV. Okay, but I mean that's unnecessary. I'm just showing you how to do it if you need to do it.